Okay, for people who are joining this live stream, we are talking about features of future versions of Wolfram Language, not 12.0, for those who are paying attention. This is about temporal logic. And so let us start off with is this going to be a giant motivation section? Oh, what is temporal logic? Yes. Okay. Propositions qualified in terms of time. Yes. Well, it's great. In principle, I am always hungry. I will eventually be hungry, except that we can't yet formulate the concept of being hungry in our language.
Right.
But so what's an example of something we would, for example, this condition will always be true. This condition will eventually be true. Those kinds of things, right?
Well, as like an entity example, you could say something like the population of France has always been greater than 1 million or something like that.
Or will eventually be whatever, yeah.
Yes, that would be an example.
Okay, so, versions in philosophy and mathematical logic. Okay. Arthur Pryor, indeed. And he wasn't even the person after whom Bayesian priors were named. Sorry, I'm just joking. Okay. Linear temporal logic is equivalent to monadic first order logic. Okay. Okay, we have an immediate question on the live stream from Brian asking if this will support Leslie Lamport's temporal logic of actions. Jan, do you know the relationship? Leslie Lamport, I remember I've run into him and he's talked about temporal logic, but I don't know. Do you know what he's done on what he did on that?
No, not really. I haven't been exploring temporal logic of actions at all.
Have you heard of it?
No, not really. I will have a look into it after the meeting, though.
Okay. I remember Leslie Lamport telling me about this stuff at some point, and who knows? Maybe it's built into LaTeX. I'm just joking. Okay, monadic first order logic. Okay, why is it relevant to tree-like structures? Why is it relevant to describing tree-like structures? I can see one-dimensional sequences, but I don't understand the tree-like claim.
Of course. So the tree-like structures come into play when we discuss different nonlinear models of time. So instead of thinking about one future, you think about all possible futures.
Okay, fine.
And think about time branching this way.
Okay. All right. Formal verification, yes. Okay. All right. Yeah. The Pentium bug. I don't know whether it's they're using a bunch of verification. I have no idea whether temporal logic. There's a British company which had this thing Z something or other. Gosh, I don't remember. That was crowing a lot around the time of the Pentium bug. That they had some formally verified something, but I don't think they were talking about using. I don't think they were using temporal logic. Do we know Roger Germanson? His PhD thesis was about some kind of verification. Do we know if it was? Do you know if he used temporal logic? Anybody know?
Yes, I've talked with him about this, and he used a version based on relations and algebraic relations, and yeah.
And how does that fit into this collection of things that you're describing?
We will see later. I think he uses the CTL version of temporal logic, not the LTL, the CTL, and he has a special way of specifying the models. But yes, let's start first distinguishing LTL from CTL.
Okay, all right. You got to be kidding me about introducing these to improve readability. Well, anyway, I think the words will improve readability. Anything that involves a random diamond showing up in the middle of something is not going to help anything.
The problem is that with words, the formulas tend to be extremely lengthy. So sometimes it's easier to have something very compact
Well, we'll see. Okay, all right. So
I mean, you can always just have it so that the make boxes, looks like that. It doesn't need to. I mean,
yeah, it doesn't need to actually be that.
That would be a problem.
But I don't think it's going to help. I think the words. I mean, it could be that the functional form isn't the best. But anyway, we're getting ahead of ourselves. Let's just. Okay, so this is linear temporal logic. Okay, true in the next moment of time. Okay, and so Nick is here, right? Who's going to be able to see how this relates to our date formalism. Is that true? Okay. All right. So always eventually be. Okay. So that means. And by the way, how does this relate to paths on graphs, which are obviously illustrating here?
Mm-hmm. So. Sorry, what was the question exactly?
Well, I didn't think I have a very good question. Can we see an example? Okay, so hold on. So then, always.
So I think we're going a bit too fast. Let's go back a bit. And so these operators are in all the literature about these, and there are two pairs. The first one is kind of trivial. Then we have the first pair, all and some, which is a bit like for all and exists. So this form a pair. And then there is the other one, the other two also forming some sort of pair. And there are this type of relations saying you can deduce all of them from two and things like that. But these are the 5 operators that are used in the literature.
So wait a minute. So what does next moment of phi mean? That's an assertion.
Yes. So the model of time that we are assuming here is a discrete model. So we have a discrete sequence of moments. And next moment phi basically means that in the next moment, phi is going to be true. At each moment, we have a certain set of propositions that are true at this moment.
Okay.
And for example, this small sequence that we have in the semantics sections, it illustrates a temporal formula, like eventually always C, together with a model of this formula. So C in this case is a logical proposition. And a model for any formula is a sequence with propositions assigned to basically each index of the sequence. And here we can see that at the starting time, propositions A and B are true. Then they become false, and then proposition C is true forever from that point. And that sequence of that sequence of worlds, because we talk about all these points at time, we refer to them as worlds. So this sequence of worlds is a model for eventually always C.
Okay, I understand. I think I have to get a little bit more. I haven't kind of seen the point yet. I mean, in other words, what's an example of a temporal logic simplification that you can do that's non-trivial, of something where you, yeah.
Mm-hmm. I think we're gonna get to more interesting examples as we go to a theorem proving section, which is in using temporal logic in Wolfram language.
Okay.
So far, it's more introducing syntax and semantics of logic.
All right. So a formula will be at the next moment, A implies B, and at the next moment A, and not B.
Yes, that's.
Why can't I put all of these things inside the next moment? Why can't I say next moment of A implies B and A and not B?
You can. That would be equivalent. That's okay. We could prove this later.
Okay. What does SNF mean? That's a normal
form.
Okay.
It's a separated normal form. It's a particular normal form that's used a lot in linear temporal logic.
Okay. So, okay, what is the implies? Well, all right, okay. I think we should go on because I don't yet really get the points here. I would like to see some more real examples, but let's just skip forward and just look through this a bit. Okay, computation tree logic. Oh my gosh. Okay.
So I think if we want to see examples, we should go to using temporal logic in Wolfram language, because first I just introduced the syntax for the corresponding logics and explained the basic semantics. There are really no non-trivial examples in this section.
Okay, all right, okay, fine. So, always, okay, so this is an assertion. What would be an analogous thing? Wait a minute. An assertion normally, if you just say P and Q, I see, that might be true, it might not be true. It depends on the state of the world and what P and Q happen to be. Okay. Always, what's the one way? It's some arbitrary predicate. Is that right?
Correct. Yeah.
Okay.
I think that we will see something interesting. I would suggest going to to the section theorem proving, and maybe first we can look at simple examples in theorem proving, because these examples here are more to just illustrate how this looks like in Wolfram language, not really to provide something non-trivial and interesting.
Okay. Okay, temporal tautology Q, not always P, is the same as eventually not P. Yes, that's true.
So, of course, these are quite simple statements, but here we are able to verify them automatically. And one use of being able to verify automatically these kinds of statements is we can use temporal logic to specify the properties of some systems that we care about. And then we can use it to specify some requirements about the systems that we care about. And then we want to prove that the temporal formula which specifies the requirements is implied by temporal formula that specifies our system, the behavior of our system.
Okay, let's try and read this one here. Start implies lives. What is that? What is the start thing? Is that a special symbol, or is that just something you introduce?
So start is a special symbol which is true at the beginning of time. So we always assume that time starts at some point. So like we switch on our system, and that's the only, that start is something that's true at
so it's like the minus infinity on the number line or something.
Something like this.
Okay. So what does start implies lives?
So it means that that lives is true at the start. So we are thinking about the sequence of moments, and there is a first moment. It's better to think about this as a natural numbers.
So why isn't it like is true at, or is true at time, or something like that?
I mean, I think you probably could do that, but it's just that you can also easily encode it with an implies.
Yes.
But I don't understand that this isn't I mean, the thing about implies is you're expecting a proposition in implies.
It is a proposition. It's saying that if start is true, then lives is also true, right? And start is only true at the very first moment. So it's saying if you're in the very first moment, then lives is true.
Right. Okay. So, but from our point of view of language design, the symbol start doesn't. I mean, are you claiming that the symbol start is sort of analogous to a symbol like true?
Oh, yes, and it's very, very standard in temporal logic literature.
I don't care. I mean, it's not going to help. We're not going to be able to have a symbol called start. It's not going to happen. So we have to figure out what the
first moment.
Well, starting moment, but even that doesn't seem right because it's a predicate, not a predicate. It's a proposition, and starting moment doesn't sound like a proposition. I mean,
yeah. Eventually, we should be able to add here the actual dates, so people would just use a date or something that is the notes.
Okay, but then it's totally weird to have, look, what would be the wrapper? Assuming there was a date here, and something implies lives, isn't it?
So
is currently, is at time, and then, or is such and such a time, and then a date. Is that what it is? What's the actual proposition that's going to imply lives? Do you get what I'm asking?
Yes.
So the proposition is we are at the beginning of time.
No, okay, but we are at a given time. So
yes.
So it's like is is at time. That's very badly said, but that's roughly what it is at a time. And then this could be last Saturday, and then this could then be saying, last Saturday, let's see, that will be a specific date, last Saturday or something. But okay, let me try and understand the rest of this, okay? Mm-hmm. So is that date implies lives, and lives implies not dead, and what? Oh, I see. If dead, then next moment of dead. If you're dead, you're still dead. And if lives implies eventually dead. Okay. Okay, so that's encoding. It's encoding the fact that, in a state transition diagram, you would go from the live state to the dead state eventually.
Mm-hmm.
So what is the analogy? What is the analog of like state transition diagrams versus these kinds of logic statements?
Oh, they are very closely related. In fact, state transition diagrams can be also models for these formulas. And we say, well, basically, for any state transition diagram, we can ask about, for any formula, we can correspond a state transition diagram.
Okay.
They are actually in bijection with each other. And on the other hand, we can ask whether a property holds over a state transition diagram, which is exactly the point of model checking, which is shown later in the presentation.
Okay. Okay.
So here we are just showing some very, very simple theorem proving capabilities.
Oh boy. I mean, is it the case that when people really use this stuff, are they really going to use temporal logic, or are they going to use state transition diagrams?
I think that what they do a lot is they do model checking. I think that's the main use case in the industry. And this is mainly state transition diagram as a model of their system. And then there's a temporal logic formula as their requirements about the system. So they use kind of combination of both. For the system to model it, they use state transition diagram, and then they have something that they want from this system, and that's more convenient to model in logic.
Okay, so let's understand in our case. Okay, so then another thing is Petri nets. I'd like to understand. Do you understand the relationship of this to those guys?
No, not really.
Okay. I mean, my question is, okay, so let's talk about some very mundane things of ours, like recurring events represented in. Does this help with representing recurring events?
I think it does. We could say, for example, that some event happens, that always eventually something happens. So it means that it will happen infinitely many times in the future.
Yeah.
Yes, but I think Stephen is thinking about how do you specify every Wednesday or something like that. So I don't think.
Okay, so
that's at this level.
Well, couldn't you say something like, I mean, you could just say, if the date today is Wednesday, that implies something, right?
Yes, we could do this. And there are also, well, I haven't really dived into this yet, but there are more complicated versions of temporal logic. Basically, temporal logic is a bit of an umbrella term for many different formal languages. And there are varieties of temporal logic called timed temporal logic, which are more exotic, but they are designed to tackle these kinds of problems. like refer to particular intervals between events and so on.
So I mean, one of the reasons we got into the temporal logic business in the first place is because we imagine that there are, practical applications of this stuff that a somewhat low-hanging fruit. Just like you could say, well, we can implement, propositional logic, and we could do that as a formal matter just for the sake of having propositional logic, but it's super useful to be able to say if A and B, blah, blah, blah. Am I making sense? So the question is, for this, the sort of everyday uses of this, not for the sake of doing things specifically in temporal logic. I'm trying to understand what those are in our system. Now, clearly, one thing is assertions of various kinds.
Mm-hmm.
We could imagine, always, well, as you have them here, always x greater than 4 or something, which is very similar to assert x greater than 4, but it has a slightly different character because it's something where you'd say, given this program, well, in fact, this is exactly the example you're now showing here. I don't understand this. I mean, so for this, you have to have multiple levels of stuff going on. You have to have a symbolic representation for the code, and then you're basically proving an assertion relative to that symbolic representation, right? But since we don't have a symbolic representation at the level, well, I mean, we do, but it isn't, go ahead. Well,
so yeah, what's happening here is we are having a code, and we can construct a function that basically takes a raw code and then produces a temporal formula that describes the behavior of this code. And then what we want to do is we want to prove certain properties from this temporal formula. And these properties have to be specified.
But we're never realistically going to be able to do this for any serious program.
Well, of course, there's all kinds of problems with bigger software.
No, but I mean, is this a toy, or is this something which is actually going to be useful? I mean, I'm trying to understand. Mm-hmm. Okay, so the reason we got into this is because, well, let me just try to understand. So Nick, for example, was working on recurring events, right? Mm-hmm. And being able to say things like, this happens every Wednesday since the beginning of time. Mm-hmm. Or this happens every Wednesday since, January of 1990. Okay? Mm-hmm. So, I mean, roughly, we then have certain temporal specifications. So, I mean, let's imagine that we say, now, do you have, Nick, yet a representation of the recurring event? Let's say, do you have any representations of these recurring events?
We don't. I mean, we have a general. I think it's still in the repository. I think there's a futurized ref page for date select. Double check.
Okay. Encouragingly, Brian on our live stream is saying this is useful.
Mm-hmm. Yeah, I mean, from what I've looked at, there is some crossover between like scheduling problems and temporal logic, but it tends to be a little more restricted.
Well, let's try to understand it, okay?
There may be, it's useful if I say, here is this date pattern, will a date within the next 100 years satisfy that? We need that for some basic arithmetic operations. Like if I say, here's my holiday specification, I want to know the next time this holiday happens, you can provide holiday specifications that do not ever resolve. And so we need some sort of formalism to check and say, they're
right.
trivial.
But I mean, date select is an explicit selector. It is not saying, given the timeline, so to speak, this will slice out just those moments in the timeline for which blah, blah, blah.
Right. And the notation we have currently that we're experimenting with is the criteria notation, which is named slots that refer to date elements. We've looked at having potentially things like a date object with an underscore to mean any month or any year, but that syntax is somewhat limiting. And so,
okay, so let's just understand what we're talking about here. So one thing would be a date object where I understand that that's overly limiting, right? So we could say date object of any year, and then, like January 1st of any year.
Yeah.
Something like that. Okay. And now your point is, if we say, let's try to encode the first Monday of every month,
Mm-hmm.
right? You've got to be able to find some way to encode that. And have you figured out some way to encode that?
Well, weekdays get particularly tricky. So the closest thing that we have to this in a real application is scheduling notation. So, the cron specification basically has a date like format, and they have an extra parameter for the day of week, because a lot of scheduling is related around that.
Right.
We can test and say, is the day name Monday? And then we have to do some more elaborate syntax to say, and are there no prior Mondays within that given month? Which,
that's a mess.
Yeah.
Right.
Or we have some sort of hacky notation that says.
By the way, we got a bunch of weird background noise. If somebody could adjust things so we don't have that, would be great. Okay. So your claim is, hey, maybe it's Jan. Maybe you should. Do you have it like a headset or something where you can actually be closer to your microphone rather than being?
Is it clear now?
Yeah, it is.
Can you hear me clearly now?
Yes, I can hear you just fine. Okay. Okay. So one set of problems we're trying to solve are these things like first Monday of every month. I understand those types of problems. I don't know how related those are to. Okay, then explain to me over here. These are things like encoding. Boy, oh boy, oh boy.
To me, this is more like order topological relations in which we specify how things work, and then we ask questions which are basically concurrency questions. Can these things happen at the same time? Yeah. Can we guarantee that this will not happen at the same time?
Okay, so I mean, roughly in the temporal logic case, what you have is some assertion, assertion about the world, and then you're asking. I guess this is, and then you ask questions based on that. Is that fair?
Right.
That is fair, but the major application, which we haven't touched upon yet, is also model checking, where you have your a system modeled by basically finite state machine, and then you ask about you then ask questions in temporal logic about this. So if you scroll down a little bit. Example?
Yeah.
That would be the very minimal example for this use case of temporal logic. So this diagram here, it represents a microwave design. Yeah, and you can see that it has a couple of states, and at each state, there are propositions that are true at a given state. And then you're interested if basically certain properties hold. So for example, in this case, you can be
I get it. Mm-hmm. I mean, so how does this relate to, for example, UML diagrams and so on? I mean, so this is like this is a sort of generalized flow chart. Do you know how it relates to UML?
No, not really.
So I mean, typical stuff for UML, right? Is these kinds of things. People, I mean, there's certain industries where I don't know what that is. That's some. Where's an example of UML? Diagram, structure diagrams, behavior diagrams. That seems relevant.
Yes, I believe that you could basically you specify this UML diagram and ask questions in temporal logic about this and do model checking.
Okay, but for example, in UML, do we have examples? Oh yeah, this is right. So when we make UX designs and things, we end up with those kinds of diagrams. And in particular, in what is it? This thing called Xure, which we use for some that we use for UX mockups. I'm just trying to understand how we will actually use anything based on this. I mean, in other words, one of those UML things, are we able to import UML? Is UML importable into some format that, I mean, what does a typical UML diagram represented as in the wild? Do you understand my question? And maybe do we know if Roger is around today? Anybody know? Somebody try
I think he's busy, but okay. we could try.
The other person who might, I mean, if we're going to talk about, okay, let's see. What does a UML file format look like? Anybody know? I mean, UML exchange format, UXF. This is pretty obscure. I mean, great. UXF is hardly a popular, there's one Wikipedia article about it, and then it, okay. But I know people build these very big UML models for particularly seems to be, I don't know, in the defense industry and things like that. They particularly seem keen on it. Okay. Okay, so Brian on our live stream is talking about the Leslie Lamport TLA plus thing, and talking about showing an example of a FIFO, first in, first out, and dining philosophers. Used for modeling, asynchronous systems like memory controllers, yes. Been lots of work done on TLA plus and plus call for writing TLA programs. Well, okay. Not stuff I know about. Let's see. The TLA homepage. Okay, so this is a language. Click here to find out what TLA is. Okay, great. Can we see a sample program? That was from 2012. Oh, for goodness sake. Okay. Specification of a resource allocator. Oh my God, where are we going to go here? All right. Allocator implementation.tla. This is pretty, I don't know. Okay, TLA plus is the newer version. All right, let's go search for that. What is TLA plus? Is it hard to use? Okay. Looks pretty much like what we saw before. Okay, assertions and stats. Hey, Jan, please, could you try to adjust your audio so we don't keep hearing some weird clank?
Of course, I can try, but there's not much I can do. I mean, I'm not doing anything.
Fine. Okay. Okay, so this is a whole complicated world of unclear. What do we think the minimal examples in our kind of serious usage for this will actually be?
I'm thinking of things like when Michael works on food recipes, imagine things like asking whether you are going to be able to do the whole thing with a single pan or something like that, or you will be able to do two given things at the same time.
Right. Okay, so your claim is, all right, so what are some things that feed into this? There's this TLA plus thing, there's whatever, I mean, there's DFAs and so on, which we still don't, I mean, have a standard representation of. There's things like recipes, procedures.
I know that people in industry actually build finite state machine models for actual programs in languages like C or Java, and then use model verification on them.
Yeah, I know. People have been claiming that for years. It happens in all of 6 cases in real life, in my observation. Brian, our live stream is promoting the TLA plus as being indispensable for modeling complex asynchronous systems. I can believe it. It just looks like a lot of work. It looks complicated, and it looks like the question is what we can contribute to because there's got to be a way of getting your. I mean, let's say you have a protocol. What is this noise? It's just driving me nuts. That I can simulate it. That's more or less what it sounds like.
I can't hear this mysterious noise.
Well,
I also hear the noise.
Well, then, Christopher, then that implicates you, I'm afraid.
I'm on mute though.
Oh, well, that doesn't do that. Okay. Okay, but coming back to this, my question is, where does one get? If there are specifications, like, for instance, I can absolutely imagine that there are, I don't know, the checkout in our store, for example, has some diagram like this that represents it, right? The question is, in what form is that diagram represented? And if we can get that into something where we can start doing reasoning on it, then it's interesting. But, how do we actually do that? Do you get what I'm saying? I mean, where does it come from? Where do we get that material from?
So I think there were 2 questions. One is, how do you represent this? And the other one was, where do we get interesting use cases, right?
Yeah.
Yes. So in terms of use cases, I mean, just thinking about this abstractly, in computer science, there are like, for example, DFAs are all over the place, and finite state machines are all over the place.
Sure.
So
yeah, but they're not. There is no very obvious representation of those things where there's boatloads of them that come to us. I mean, I've generated lots of DFAs in my life from cellular automata, which is some completely bizarre case of them, right? The case of right now we don't have a standardized DFA representation in the language. You know what? I think what's not muted is the person who's hosting this. Okay, go ahead.
Yes, I would have to think about particular examples. I know that one thing in the industry that it's used a lot is hardware design.
Yeah, sure. Brian is saying that he'd love to have TLA plus capabilities in Mathematica the next time he needs to model an ASIC that he's architecting.
Yeah.
Fair enough. But so the question is, in what form would you have the specification of that ASIC? That's the thing I'm asking. I mean, if it's in Verilog, I don't know what ASICs are specified in, Verilog or something like that. But that's a whole nother, set of conversions and things one has to represent there, I would think. Okay, but anyway, we should probably go ahead. Yeah.
Yeah, the question of the language for specifying this is something we've discussed today with Jose, that we will have to, that's something we will have to think about deeper. Like, what is presented here is obviously some very, very provisional representation, which just takes a graph and models this. as a graph in mathematical language. But as you get like huge numbers of states, and if we want to model hardware or software, we're talking like thousands or even millions.
That's not the problem. The problem is, how do you ever get any input that anybody's ever really going to type in that engages with this? Okay, because nobody's going to type in, the way you get something like this, it's got to have there's got to be some source of this that isn't just somebody typing this in. And the question is, what on earth is that going to be? Is there some place where somebody has already built the specification? For example, they've already built it because they're mocking up a UX, right?
Yes. So I presume, I don't know much about hardware design, but I presume that people don't draw the diagrams on the piece of paper. So they
it's probably done in Verilog, I would guess, or something like that.
Yes, so we would have to have some interface, some way to interface.
I know, but the problem is there's many other things you have to represent there. Do you get what I'm saying? Than just this. This isn't enough. Get what I'm saying?
I see.
It's not really useful because it's the fact that the Verilog tutorial looks like this is there a more recent version of all of this stuff?
Well, yes, I don't know Verilog at all, so it's hard to me to comment on this. What could be to model?
Yeah, but this isn't a problem we can solve here, because what is this background noise? It's just driving me nuts. Does nobody else hear this?
I can hear it, yes.
Okay. Okay. The thing in terms of prioritizing what projects we do, a project that involves the only way people ever get to this is they typed in a 50-page, a huge input that didn't come from somewhere else. I mean, something like you could say, well, image processing, image processing, as soon as you've got a way to get a picture, let's take audio processing, okay? If we didn't have a way to get audio into the system, audio processing would not be terribly useful. I mean, for a long time, so I'm just trying to ask, how would you get, how do you get this stuff in? Or if that's not what's going on, how are we using these ideas to deal with very, this is what you're generating. Come on, doing simple things like, first Monday of every month and so on.
So answering to the first question, I don't know the answer off the top of my head, but people in industry claim they are using this for hardware verification.
I understand that, but then we don't. I mean, okay, that's because they've got their hardware specified in some language. I don't know these languages, like Verilog or something. Okay, it's its own whole complicated world. It's got it. It turns into things that relate to how system modeler works. It turns into things like modeling, how a particular capacitor works and so on. That's a completely different story from this. Yes, there is logic stuff that you can then try and prove things about using these methods, but that's a really thin, you have to find some way to extract from that into something useful here, because this representation, this symbolic representation, is going to be nothing like what comes out of the, the pure raw, hardware design specification. At least that would be my assumption. I mean, it's analogous to, this is analogous. If you say it's like hardware stuff, I mean, okay, great. We can look at that. We can just say, if we say something like this, I mean, we can look at, I'm sorry, I must be, I think it's some bizarre, this background noise is just driving me nuts.
Maybe I'll try to, if it's generated by me, I will try to just mute my microphone when I'm not speaking.
Yeah, you can do that. Will help. Okay, so let's look at an example here and see what it turns into, because I claim what this turns into normally is systems of equations. But there is also another more logical representation of what's going on. And we have completely the wrong set of people here to discuss this. But I mean, I didn't think at all we were going to go in this direction. I mean, I understand this is a high-end application of temporal logic, but let's see. Oh, for goodness sake. Well, that's got not only logic, but also actual this is such an ugly browser. Wow. Really. Hopefully this will get fixed soon. Okay. So I don't know, let's try a 8-bit adder here. It's kind of weird. Okay, digital 8-bit adder. All right, let's try this. What does that mean? Let's copy it. Is that just a single block that is an adder? That's really weird.
I think you can go inside of it and see that it has subcomponents.
How do you get to the subcomponents?
I don't know how you get to them in Mathematica. In System Model, I think you like double-clicked or something.
Yeah, I mean, here we've got, why this doesn't auto-complete, I have no idea. And that probably should be reported as a bug. If somebody could do that, that would be great.
I'll know that's true.
Okay. So this should be generating whatever the equations are for this. But I mean, this is the type of thing where you would expect this would have, if this is all going to connect together, this would have some temporal logic representation, presumably. I mean, the trouble is that system model is fundamentally about equations which tell you about the instantaneous state for all times of a particular system, if that makes sense. Whereas temporal logic is telling you, I mean, it's sort of a program is telling you this happens, then this happens, then this happens, typically.
Well, system modeler is a special case of temporal logic. It's the case where you just say that such and such a state implies that such and such a state will be true in the next moment.
Yeah, that's true. I mean, you could think about it that way, I suppose, assuming that the equations have that kind of character of being initial value equations. So this is a big mess. So this didn't work. So Manu, if you could try and report this also.
Sure.
Okay. All right. Let's come back then to. Let's come back to the original. So I'm not, in my attempt to orient myself about how this is going to be used, I've been a bit unsuccessful. But let's come back to the original topic of. Okay, so you're saying there's temporal tautology, temporal satisfiable. In other words, is there an assignment of, are they truth values? What are you assigning to, or is it histories that you're assigning to, the P's and Q's of temporal logic? What are the primitives of temporal logic?
Yes, the analogy of the assignment of true values to variables in Boolean logic would be a sequence of worlds in temporal logic. In other words, assignment of true propositions to each state, to each world in the sequence of worlds that represents time.
Okay, but so
clear?
Well, maybe. I mean, so what you're saying is there's a proposition P, it's raining, for example. And instead of there being, normally we would have something where we say, okay, so we're talking about what the variables are here. So, I mean, normally we would just say P is a proposition that means, it is raining. But what you're saying in temporal logic is that it means that P is a whole family of statements. It's like, what? Yeah, go ahead.
Not really. Rather that we have a sequence of worlds, and P can be true in some of them and false in others. Whereas in Boolean logic, P is like always true. P is just true or false. But in temporal logic.
But I mean, so a naive thing would be to say we have okay, so this is another place where this temporal logic is relevant, okay, which should have been brought up here, is in time series. Because in a time series, for example, we just had this issue. What the heck was the issue? We just had this issue with the time series. So here's the point with the time series. Normally with a time series, you say, blah is the value at time X, time T, right? But sometimes what you want to do is you want to say that value will continue until such and such a thing happens. So we just had this. What was this for? Oh, I remember what it was. We were looking at historical countries, right? And we were asking the question, if you have a historical country and we know that in 1847, the country was invaded or something. The polygon we have, so this is the very practical example. The polygon from 1830 to 1847, we know the polygon in 1830, and we want that polygon to continue to be in effect until the event happens in 1847. You see what I'm saying?
I think you could technically do that with a time series of interpolation order arrow 0. But time series, like I remember I did this. I was doing this exact thing where I was representing historical countries. And at one point I tried representing them with time series with interpolation order 0, which worked and which did that. Although it had some other very weird, funky consequences.
So I think that there's things like left hold and right hold and things like this, where you're saying the thing should be equal to what it was at the beginning of the period and such like.
Wait, do you mean in this temporal logic? You mean time series?
In time series. Because I'm trying to understand, what is the relationship between...
But that's kind of what, okay, at least left hold is basically what you're saying.
Yes, that's correct.
Is the default. And otherwise you can do right holds just by shifting everything over.
Yeah, that's true.
And putting one thing at time negative infinity, which I'm pretty sure you can do.
Fair enough. Yeah, I mean, Brian on our live stream is pointing out that a temporal logic specification could be converted into a controller object would be super cool, but that's a whole different, I mean, if we compare that, again, we're looking at other comparables. I mean, we've got our microcontroller kit. So let's understand the relationship. I'm sorry, I'm still trying to, oh, that's disappointing. Where is the microcontroller kit? Did I spell something wrong? That's really weird. Isn't this in the documentation now? I wonder if it hasn't been committed. That's really weird. Manu, it's another issue.
Yes, John.
What is going on here? Something is very wrong. This is well, okay, so I misspelled microcontroller, although the fact that our spelling corrector can't deal with that is pathetic. Okay, so that generates that there are two issues there. One was a stupid thing of the spell corrector so that may be getting fixed for other reasons. Okay, so let's just try to understand this. What is the relationship? Boy, there's so much stuff I don't know. A state space model or this transfer function model, what is the relationship with any of this stuff to, I mean, these are all, given a continuous input, this is the continuous output that's produced. These are not these things that say there are discrete events that lead to other events, I think. But this is a model, so you could imagine, I suppose, something where you have a specification in your, of essentially something like a state transition diagram or this piece of temporal logic. And then you could imagine, I suppose, although it seems exotic to figure out how to connect everything up, to say there's going to be certain inputs that you connect things to. Boy. Yeah, I mean, I have no idea whether you can actually write. Okay, look, I think I'm still a bit disoriented, but this is the first time we've talked about temporal logic, so that's
right. I would say that the other things we were discussing were more related to differential equations events that happened at a given time, things like that. Well, in temporal logic here, we are discussing more like relations of things that we don't know exactly when they happen, but we know that one happens before the other one.
Yeah.
And so we are interested in knowing whether they will.
No, I mean, clearly, right. So clearly for kind of common sense reasoning type stuff, for whatever good that is, this stuff is useful. And having, I mean, what do we know about the spatial analog of this? Such and such is inside such and such is on top of such, and so on. Do we know anything about that? There must be a similar, I know there is a similar kind of logic for spatial purposes.
Well, this is one-dimensional, so the only thing I can relate to this is Allen algebra of intervals. Okay.
Well, that's a whole nother issue, right? I mean, is one interval greater than another interval? Do they overlap? So what is the analog of that in temporal logic? If I can define an interval of time, okay, how do I define an interval of time here?
Well, there's no such thing as an interval, but you can say this happens until the other one. So you know that it will be before. So it's more like relations rather than actual numbers.
Yes. But I mean, for us, again, to be practical here. Okay, so okay, let's just look again at so this is dates, etc., right? So we might have a date interval here, and then we might want to ask the question, what's the analog of this? I'm still trying to there's a simple question of, is this date interval completely before? What's the analog of this? Continues to be true up until blah, blah, blah. There must be some analog of that. Is this date interval completely before some other date interval?
Perhaps the analogy with first-order logic, Jan, could be useful here, because this is a bit like first-order logic together with some inequalities.
Well, yes, that's true, but it depends. What do you mean by date interval? Do you mean here
a concrete interval of time?
Mm-hmm.
Next.
And do you treat time here as a sequence or as a continuous model of time?
It might be granular if we have granularity in there, but I would say it was But what's your point? I mean, the thing I'm trying to do is to say, is this interval completely okay? So, for example, does interval 2 start before the end of interval 1? How would we say that? And is this kind of representation of, is that useful to this?
I know that people mix interval algebra with temporal logic, but I think we would need a more extended version than the standard LTL. For example, we would need also a way to referring to the past. So if you are in some point and you want to talk about the interval, you want also to talk about moments before this point, and this is possible as well.
Okay, but I'm trying to understand, in practice, okay, if we implement all this stuff, right?
Yes.
How are people going to use it? And I'm trying to understand these types of things, like date intervals we're about to have, and I think date intervals we clearly know are useful because there's plenty of things where, and so.
So I initially
go ahead.
So I initially focused on the applications that I knew are most used by the industry.
I know, but I don't believe this industry applications thing, okay?
Of course.
I believe that the problem is something like circuit design, there's a giant stack of technology used for that. It's, we don't have most of what's there, not our business, not the right thing to focus on, right? The case that's interesting to us is the case where the technology of temporal logic intersects with things that often will never have been done before, that have run, that we've run into through, for example, the fact that we have a larger knowledge base, the fact that we represent things like historical countries, which are not things that, or we're representing things like, I don't know, complicated date specifications that are relevant for, finance computations, things like this. These are things where, rather than trying to emulate some giant stack of stuff about, circuit, verification, which I just don't think, in the case of Boolean algebra, for example, we have fine state-of-the-art stuff for doing things like satisfiability in Boolean algebra. And that is occasionally, very useful to people, but it's not going to be something. In order to use it to do circuit stuff, you have to have a big stack of other things that's not really our business. Okay, so what I had thought with temporal logic was, and I still think, that for a lot of the things we want to do, for example, the things I want to do eventually with the whole symbolic discourse language business, where you can take, everyday statements, about things, let's say in English, and write them in a more formal way, this can be useful for that, so long as it's a decent model. So cautionary tale, okay?
Yes,
back in the day, people thought propositional logic and then predicate logic would be a way of representing all human knowledge. Turned out to be a pretty stupid idea. In other words, there's, the whole, you can start writing 50,000 predicate logic statements about the world, and that's turned out nobody has found that terribly useful. It's just not a very good representation. Yeah, but Brian on our live stream is pointing out that Microsoft and Amazon use temporal logic to validate the design of their database systems. I don't doubt it. And similarly, I don't doubt it. There's no question that, we could use it to do things with validating UX designs, right? If we could only get those UX designs into a form that we could compute with in some reasonable way, right? Because, and then we have to think about it. Let's say it was a UX design for a store checkout, okay? What is the native form of that UX design? So eventually that store checkout is going to turn into random web code, okay? But see, again, we have the wrong people on this call, but
this may be a bit like graph theory in the sense that people will have to find their ways into constructing the graph. And here we have a directed graph. Then we can reason about, is it possible to find paths for which this thing happens? Or
yes.
Is it a property that will happen for all the directed paths to the graph?
Right. I think that's a good analogy. Right. It's like you can take, so let's just say, getting whatever they might be called, temporal specifications or something, which are essentially flowcharts, etc.
Right. So this CTL version, it's just generic computations with trees, with directed trees.
Right. But so to give an example, right? So this is a tool that our UX design folks sometimes use. Okay. So conditional flow. Oh my gosh, you can't even click on this. Wow, that's weird. Okay, so there we go. So that's a typical, the UX group often produces these unbelievably complicated diagrams, which I can't understand. But that's what they're doing, is something like that. Okay. Okay. So yeah. My question is, so to me, this is exactly the type of thing you're talking about.
Yes, I think that would be directly applicable to this.
Okay. But the problem is
about this graphs, but
right. But the problem is the way people normally do it. It was the same with like Visio is another example, I think, of a thing that has a little bit less semantics than this. That where there's a specification and it's represented in this graph, but then I take your point that if we can ever get the graph out as a graph, Okay, so let's understand the analog to the graph. Okay, so we could have a graph whose states, we'll have some random graph.
I also wouldn't like to focus so much on specifying the transition system as a graph. I mean, in terms of just how we specify the transition system, we can have much more flexibility.
I understand that, but I'm saying there's a source of boatloads of these things. Okay, if you can get out of something like this a graph, right? I mean, this thing will eventually be some labeled graph where there is semantics, like those are probably conditionals, right?
Yes.
If I remember my flowcharts, right? So the question is, if there is some reasonable way, but so here we don't have any such thing. Our graph is just a graph. The fact that the output of that node has 4, valence 4 is irrelevant to it's just a graph. It just says, hi, I'm connected to these other nodes, right? Has no semantics.
We need some labeling on this graph.
Yeah, sure. But I mean, so if we have a directed graph, we have one. So I mean, I think, again, this is, look, we've got the concept of a directed graph. We've got the, beyond the directed graph, we've got sort of a finite state machine, I guess. Beyond that, we've got things like Petri nets, I think.
And what about these Bushy automata?
Yes, Bushy automata are basically used for. I don't think they are relevant here. There are something that there are kind of automata that represent temporal formula. So it's
what is that? But these things? Is that what?
Yes.
Is that the right spelling?
Without S.
What's that?
That's a certain kind of an automata that recognizes infinite languages.
Yes, I remember that. Right.
I think it's without the S.
Without the S?
No, sorry. It's without the S. Exactly like this.
Okay. Whatever. Yeah. Okay. Okay, but imagine that we had some UX specification. Then what would we want to, that UX specification looks like a graph, but somehow, I mean, oh gosh. See, we could represent a graph. Okay, so given a graph, we could say there are a bunch of relations: rel, AB, rel, BC, rel, AD, those kinds of things, right? That is a way to represent a graph. Does that make sense? I mean, alternatively, we can just say to this, we can just say, instead of rel, we call that rule, and then that whole thing is a graph, and sure enough, it will be a graph. Not a very exciting graph, but it's a graph, right?
Indeed.
And so what you're saying is, what are the nodes? I mean, in your thing, I'm confused about what, in a diagram like this, your statement P, for example, where it says always P or something, what relationship does that P have to things in this graph?
Okay, so at each node at the graph, we have to specify what is true in this state. So each node represents some state, and some things are true in the state. One thing that can be true is the name of the state. It can state can be uniquely identified by the proposition that says it is the state of this name. But so what I'm saying with temporal logic is we pick some node that we start from, and we say that something holds on all possible paths from this node.
Okay.
So, for example, I say that if I start from this node, then whatever path I take, until I get to some state, something will be true.
Okay, let me give an example. Okay, we'll talk about a store checkout. Right? It better be true of a store checkout that you can eventually check out.
Yes, it's better be true.
Right. Otherwise, it's not a good business proposition, so to speak.
Yeah, I agree.
You might also want a property that says you can always cancel any transaction until you check out. Okay.
Yes.
So now the question would be, and by the way, another thing, obviously, okay, so let me give another example of temporal logic that I can imagine, which maybe is similar to what Brian was talking about. As soon as we start doing not just reading relational database stuff, but also writing relational database stuff, there is the question of whether you respect, atomicity and all this kind of thing properly. And one could certainly imagine representing that in terms of this, first you do this, you write this piece of data, you do that, and you say, will you ever be able to get into a situation where you can corrupt the data? I think that's a similar kind of problem.
Yes, I agree.
But the thing that I'm having a hard time with is, how does one get from the piece of code that represents all that stuff to something that you can actually work with in temporal logic? I mean, the trouble is, okay, let me give another example. So we are just about at the point. So you can derive a call graph for, from a bunch of Wolfram language code. We're not the world's easiest language to derive a call graph from, because obviously we have dynamic code and things. But let's assume that we do have stuff to ingest like large C programs and derive their call graphs. So there we get a nice graph from the wild. And so we might be able to ask a question like, is the piece of code dead, in the sense that it can't be reached from any place that is an exterior node?
I think that one thing that would be very useful to check is, for example, if we have some concurrent software, is there a deadlock or something like this?
Be wonderful. But the question is, in what do you represent? This is what, I'm sure this TLA plus thing is a way of specifically representing that. I expect, naive thought would be that in some language like Erlang, that there would be some way of taking Erlang code and running some verifier that determines whether you can have deadlock. Hey, Christopher, do you know for these languages or something like Go or something, is that something people routinely do, or is the language structured so it can never happen?
Wait, sorry, is what something that people routinely do?
Check for deadlock in a Go program.
I'm not sure that. I have to think about whether you can actually get deadlock. Like if there's
it may be designed so you can't get deadlock.
I mean, obviously, if by deadlock you just mean that it stops. I mean, of course, because it's Turing complete, that could happen. It could not halt. But I mean, if you mean deadlock as in X is waiting for Y and Y is waiting for X, and so they're just sitting around, I'm pretty sure that can't happen, because each Go, like in the case of Go, right? Because that's sort of the most relevant case here. Each routine can only, well, actually, no. You could easily make a situation like that, but I mean, it would be kind of trivial. Like you could just tell one Go routine wait for something on this channel, and another Go routine wait for something on some other channel, and just if nobody writes to either channel, they'll just sit there forever.
Right. Phil on our live stream points out the temporal logic and the ask function might be an interesting combination. Automatic website flow. Yeah, that's an interesting idea. That something like ask, can it get itself into a... So, I mean, I'm understanding why this is potentially useful. The part that I'm having a hard time with and I'm trying to, grapple with is, I think your analogy with graphs is a good one, that many things turn into graphs and it is varying amounts of work to turn them into graphs and then, and then do computations on them. And, but so, places that you might get stuff from are, was I making a list of this? Yeah, I mean, at places you might get stuff, I guess would be, okay, so sources might be things like UX designs. I suppose various kinds of database / concurrent code, but, you have to have a representation of that code. What about all these things with, I mean, okay, things like the futexes and mutexes of this world, how are those represented? What is the abstract representation of those things? Hey, Christopher, do you know that? I mean, in other words, people write them in specific languages. But is there some more abstract representation? Maybe that's this TLA thing as a way of doing that.
I mean, there is an overarching. I mean, between languages, there is an overarching abstract idea of a mutex, if that's what you mean.
No, but I'm asking if you are to abstractly represent without a specific mutex that does a specific thing.
Yeah.
You're to represent the idea of a mutex. That presumably, what is, could you say, like in temporal logic language, what a mutex is? Is that sayable?
Yeah, I think so. Okay, so you need a variable that represents whether the mutex is locked. So, okay, it's like L. So I think you would just say something like, well, okay, you basically need to say that if L is, so okay, L implies that, L implies that the state of the variable right now, so let's call it A, that A imply that if the state of A is something, that it'll have the same state later. So I think you could say L implies, I don't know how we're representing this, but L implies that A biconditional next moment of A. I'm not sure if that's entirely right with the next moment thing, but something like that. And you need to make sure the parentheses, I don't know what the precedence is, if you care.
Okay. Well, so wait a minute. So
it's saying if it's locked, then A will not change between now and the next moment. If it's not locked, then all bets are off.
Okay, but so what? Is that okay, so what else is there to say about it?
I mean, I think that's it. I mean,
but then that's some other assertions, like the lock will eventually be. I mean, eventually there won't be a lock.
You don't know that. It could be locked forever. It could be locked forever. It could never lock. That's just depends on how you use it.
I understand, but for example, we have a practical problem. Okay, so this is a practical issue with cloud objects. Okay, we are considering having something where you can do critical, whatever they're called, these places where you can do updates. Oh gosh, what is this called? You know, where you guarantee that you don't corrupt the thing, a critical section or something. The thing where you say, okay, so, but we don't want the lock to last forever, because if the lock lasts forever, you've just frozen your file system.
Well, you need to do other analysis on what sets the variable L to know whether L will at some point be.
I know, but you might want to have an assertion that says eventually L will not be locked.
Well, no, but that's the whole point. You're trying to figure out if L will eventually be not locked. So you can't have that as an assertion if that's what you're trying to check. So I mean, presumably you need to encode.
Well, okay. So my guess is that we want the locks to, in practice, in the cloud object store, we want the locks to decay, right? But I suspect that a good example of a temporal logic use case is to make sure that when the lock is removed through timeout, that nothing terrible happens at that moment, right? Because something bad could happen.
I don't know if you want it to lock by, unlock by timeout, unless it's literally just someone is making a change and they time out because their connection is bad. And so
no. I mean, the thing was locked, and you're 3 days later, and your
it
code
shouldn't be like if it's 3 days later and it's still locked, there's a very fundamental bug going on.
No, but think about this: the code somebody writes says start the critical section. Okay, then for some reason, because of that code, well, I guess you're saying it's an exogenous effect because that code fails to complete.
Yeah, so and you have to know that. I mean, and right. I mean, right. And the point is, if that code fails to complete, if it crashes, then of course you should take off the lock. But I mean, the thing is that the only way you would know that is by doing analysis of the other parts of the program.
Well, but the statement, if the code crashes, you take off the lock, is already something that can be written in this more formal way.
Yeah, sure. I mean, the fundamental
because crashing is like the example Jan had earlier of of not living forever and so on. Once a piece of code crashes, it can't uncrash. So there's probably some logic. Okay, so I get the point that
if you want an example of a case where you could reason something about this mutex. So suppose that the variable that you're storing in a mutex is another mutex. It's like the lock property of another mutex, right? Then you could show that if the first mutex, if the outside mutex is locked and the inside mutex is at some point ever locked, then the inside mutex cannot unlock until the outside mutex unlocks, right? That's a random thing that you could derive. Yep. I'm not sure how useful that is, but.
Right. Okay, so look, we're going to run out of time in just moments here, unfortunately. This was a good first introduction, and I think, so in what you've done, Jan, so let me just understand what you've actually done. So you've got it so that with those primitives, you can do various kinds of reasoning. Is that correct?
Yes, in particular, we can do tautology checking, satisfiability checking, and model checking for finite state machines.
Is satisfiability checking not, is it NP complete?
Satisfiability checking here is p-space, I believe, for LTL, which means that it's X time.
Okay, because it's TQBF or whatever. It's similar to that.
What? I don't know what that is.
Okay,
but
whatever.
Yeah, it's in polynomial space, so less or equal.
The question is whether it's. Yeah. Okay. So it's some p-space complete creature, maybe.
Yes.
Okay, but so it doesn't mean in practice one can't do it. I mean, like satisfiability checking. We have a pretty good satisfiability checker, even though in principle satisfiability, well, one doesn't know how long it will really take, but it's okay.
The good thing is that model checking for CTL is polynomial time.
I'm not surprised because there's a linear, there's some kind of linear sequence in the picture. All right, listen, we should wrap this up here. Next step, I really think we got to understand a little bit more about where you get. When we did the graphs, for example, we had a pretty good understanding of where, we have a nice simple representation for graphs. They're pretty easy to type in. Here, one of the things that bothers me is that, you're having to, well, you could argue the same thing is true for Boolean expressions, that you have to invent some symbol. Yeah. I guess one difference between graphs and this is that in graphs, there are applications of graphs where every node means something, but there are also plenty of applications of graphs where just you get nodes by the boatload. And similarly with Boolean expressions, there are applications of Boolean expressions where you get essentially variables that are just abstract variables. In this case, I'm not seeing serious applications where that's the case. Is that a fair statement?
I'm not sure if I got the point with Boolean algebra here. Could you give an example of such application?
Well, I'm saying that, I can go ahead and, I can say Boolean function, 145, 3. That's just some random Boolean function. I'm not having to discuss the fact that the first variable means whether the microwave oven is on. The second variable means whether its door is open. Those kinds of things, right? They're just abstract. It's just abstract arguments to, abstract. It's an abstract thing, so to speak.
I'm not sure how is it different in temporal logic. You also could have like abstract arguments in temporal logic.
No, I understand, but so is it useful? I mean, like for example, with Boolean functions, like cellular automata would be a good application of this. Where
one very loose idea that I have is maybe that could be useful in computational contracts, for example.
Oh, that's a reasonable idea. Okay. Yeah, that's an idea that should have been in the very beginning of this discussion. Sorry.
Sorry, I actually meant to say it before, but I wanted to finish first on this automata thing.
Yeah, you're right. That's a good application. I mean, that's a good case. I mean, so for example, writing, a no double spend type condition, for instance,
Mm-hmm.
All right, we have run out of time, but finally, in the last moment, we've understood what the real. Okay, all right, I'm much more sold on it with that point. Right. Okay, we should wrap it up here then. So we'll continue, and we should pick this up again fairly soon, because I think you've been actively working on this, and we don't want you going off in sort of the wrong direction here. And I gather people are asking when the next live stream will be, and I'm not sure what the answer to that is. It's definitely going to be after Christmas. At least that's my theory, but I'm not quite sure when. All right. Well, thank you, Jan. Thank you, everybody here. Thank you, people on the live stream. Bunch of good and interesting comments, and to be continued.
Thank you.
Okay. See you.
Thanks, everyone.